Okay, I couldn't actually find this question, so I just made it up myself. State the purpose of a CPU, pause the video, give it a go yourself first. Okay, the purpose of a CPU is to simply process data, execute instructions. So it runs the instructions, what it's told to do, and it processes. That means it takes the data from the computer and it does something with it. Whatever it does, it's based on the instructions. So it processes data, executes the instruction. So if the instruction was to jump, it would jump. If the instruction was to close, it would close. The data is what it is, which needs to be changed. Process data, execute instructions. Okay, so pause the video, give this question a go first. Right, so we see this question talking about stored program concept. This is really simple. The stored program concept is where you've got a CPU which fetches one at a time data or instructions from RAM, main memory, the same memory. So data and instructions share RAM, the same memory. So how do I put this into an exam answer? Well, we know that the CPU does that cycle, fetch, decode, execute. The stored program concept is all about, as I just said, the CPU fetching one at a time from main memory data and instructions which share the same memory, i.e. RAM. Okay, so another way of talking about the CPU's fetch, decode and execute cycle is using the term von Neumann. Von Neumann's model is our traditional fetch, decode, execute model, using the stored program concept. Pause the video, give this question a go. Okay, so we looked at in the previous question this same thing. Data instructions are stored in the same memory unit. They're both stored in the main memory, the RAM. So you've got data and instructions. The control unit manages the operations within the CPU, correct? Data instructions can be fetched into the CPU at the same time. No, in stored program concept, it's only one at a time. We looked at that in the last question. Control unit is responsible for decoding instruction, true. So this question is looking at the steps of the fetch, decode, execute cycle, i.e. the von Neumann cycle. What we're meant to do is put it into order. What I'm going to do is I'm going to draw it out here. So I've got the CPU, I've then got my RAM, my main memory, and then I've got my SSD. Step 1, the program counter contains the address of the next instruction to be fetched. So let's say instruction 1. We know that we've got the MAR here, and I know that it gets copied here. So let's look to see if there's anything about copied. From the address contained, the PC is copied to the MAR. Great. Then what needs to happen is that we do our buses, but let's see if there's anything about buses in here. No, so there's no mention about buses. So we know that a bus will go to here, it will fetch, the data bus will bring it back into here, and it will put it into the MDR, the data, or the instructions. The instruction is then copied from the memory location, i.e. the RAM, into the MDR. Yep. So that'll be number 3. After the MDR, we know that it goes into the CIR instructions. So entire instructions are copied from the MDR into the CIR. We then got, now at any point after we copy it into the MAR here, from here to here, you can say that the program counter goes up by 1 or is incremented. So I'm going to put it here. So it's pointed to the next, but this could happen at any stage. So we could have put it as our step 4, and this could have been our step 5, for example. It makes no difference. So we're now in the CIR, the instruction. What happens next? Well, not only are we going to be operating here, the CPU is going to then fetch the next instruction, and that's going to be put into the MAR, or copied. So the address part of the instruction, if any, is then placed into the MAR. The if any part is if there's anything for it to execute. So we know that this has to happen, and it's not talking about this one because of the if any, because it might be that the program counter has nothing there. Very unlikely, but it might be. If it's got nothing there, then it won't copy into here. So we've got this happening, and then the instruction is finally executed. Now, after it's been decoded, we can mention about the ACC, etc. So let's imagine, I'm just going to add a little bit to this now. So we've copied it into the ACC, it's performed some sort of logic, and it's been executed. What happens next? Well, the changes, since it's been executed, so it might have had some changes, so it might be like that now, are then sent back to the MDR, which are then, using data bus, put back into the RAM, which are then saved, if needed, eventually to your SSD. But they'll be put back into the RAM with your changes. So let's imagine it was updating a Word document from A, I deleted it and I put B instead. That'll be a change. It'll then go to the MDR. The MDR will then pass it back to the RAM, and it'll say to the RAM, hey, these are our new changes. So it goes from ACC back to MDR, MDR to main memory. Okay, so this is another question to do with the von Neumann Fetch-Decode-Execute cycle. Pause the video, give it a go yourself first. Right, so let's see how this goes. Kevin correctly answers questions, blah, 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 blah. 8 different terms have been removed from his answer. Why? Why would you remove the terms? That's silly. But it's a perfect answer. Anyway, not all of these need to be used, so I'm going to cross out the ones which we've used. So, the CPU, something the data instructions needed. Well, we know that the CPU fetches. So we know that. The data instructions needed and stores them in the something waiting to be processed. Well, here's the thing. This is a bit of a, it's pretty badly written. Oh shit, my water's leaking. Oh, shoot. Okay, sorry about that. I had a water bottle which was leaking all over my computer. Not good. Anyway, so the data instructions needed stores them in. Now, our data gets stored temporarily in our main memory for it to be used, i.e. our RAM. But we don't have RAM on here, but there is another term for RAM, well, memory for CPU, and that is the IAS. It's not really used anymore as a terminology, but that is basically saying the same thing, immediate access store, because it waits in the RAM for it to be executed or processed by the CPU. The something holds the address of the next instruction. Well, it could be MAR, but it also could be PC. Now, it's going to be the PC. The program counter holds the address of the next instruction. This address is then sent to the, so it goes from the program counter, as we know, and copied to the MAR. The data from this address is then sent to the, so we go to the address, we get the data, and we send it to the MDR. We've done that, and we've done that. The instruction can then be decoded and then finally executed. Any calculations are carried out by the, well, it's the component called the ALU with a arithmetic logic unit. When it's doing the calculations and logic, etc., it stores the data temporarily in a register called the accumulator, the ACC. When it gets executed, it then goes to the MDR, and from the MDR, it gets put back into RAM with the changes. Okay, so this question's a little bit harder as it's not giving you any words to play from, so you've just got to recognize what it's asking of you. So pause the video, give it a go yourself first. The von Neumann model for a computer system uses the something program concept. Program concept, what would that be? Well, it's obviously going to be the stored program concept. A program is a series of instructions, great, that are saved in where? Well, we know that you've got a CPU, we know that you've got a program. The program, an app, whatever you want to call it, an application, is stored or saved in main memory. Our CPU, the processor, the CPU, something each instruction. Well, we know it's going to fetch. So it fetches each instruction. Once it's fetched it, we know it's going to decode. Once it's decoded it, we know it wants to execute it. The CPU uses something to store data. Well, we know that is registers which store data in a CPU. So you've got all the different registers. Each one's job is to store data. The reason why this was slightly harder is because it's actually an A-level question. Okay, pause the video, give this question a go yourself first. Briefly describe von Neumann's architecture. Well, we know that it is a CPU which follows the fetch, decode, execute cycle in order. So it's one CPU that follows the fetch, decode, execute cycle in, we can say, like a sequence. So it follows a sequence. It fetches from memory and stores data, addresses, in registers in the CPU. Addresses are basically memory locations in the CPU. So it's memory for the CPU. So how would I put that into a nice answer? Let's do it. Okay, so von Neumann architecture is one CPU that follows the sequence of fetch, decode, execute cycle. And I'll put in brackets stored program concept. Data, instructions are stored, well, fetched and stored in CPU registers, and the registers are memory locations. Okay, so this is another Fetch-Decode-Execute cycle question. It's a huge one, so let's get going. Pause the video, give it a go yourself first. Okay, so I'm just going to do this quickly because we've done similar questions to this already, but we know that it will be CPU, you've got the program counter, which will copy the address of, I do AONF, address of instruction I, AOINF, address of instruction which is needed to be fetched next, and it copies it to the MAR. From the MAR you have the address bus, which fetches the instruction from the address location in the main memory or RAM. Location, keyword, key. The data bus will copy it to the MDR, the instruction. The MDR will then give it to the CIR. In a CIR, it will get decoded by the control unit. From the CIR, it will go to the ACC, where it will store the data, whilst the ALU will perform logical operations on it for it to be executed. When it gets executed, the result from the ACC will get copied to the MDR. From the MDR, the data bus will take it back to the RAM, where it will get stored in location to show the changes. Pause the video, give this question a go yourself first. Okay, how would I do this? I would draw out very quickly my CPU, I'll do my PCC, I'll do my MAR, I'll do my MDR, I'll do my control unit, I'll do my CIR, I'll do my ACC, and my ACC is inside the ALU. Now let's go to the question. Identify a component within the CPU that the accumulator is built into. And so there's two parts of this question. You've got that, you've got the and then you've got to describe the purpose of the accumulator. Well, we know that the accumulator is built, or is it inside the ALU, which is the arithmetic. I can't spell for chicken. That says arithmetic logic unit. Great. So that's that bit done. Describe the purpose of the ACC and this is important, temporary, because temporary memory. Store data, that's what registers do. What is that? It stores data. What? I can't even get rid of this. That is so weird. Let me erase it this way. Okay, stores data for the calculation / logic and its results. So let's say, for example, it had, I'm going to make this really simple, 4 at 4 in here. It gets decoded at CIR, it gets then executed here, so it'll, and the instruction is add. It'll make it 8, so 8, the result will go into here. As we know, once it's done that, it'll go to the MDR will then pass it to the RAM using the data bus, and then the 8 will be in there. But my point being is, the purpose of the ACC is to temporarily store the calculations / logic and its new results once it's been executed. Once it's done its job, there might be instruction to say wipe it clean, because we're going to deal with something else now. Pause the video, give this a go yourself first. Okay, let's do a solution. How would I go about this? Well, I would actually write down all the components of the CPU first. So we've got MDR, CIR, accumulator, control unit. Am I missing any? ALU. I'm then going to do the ones where it's done the hard work for me. Bam, bang, and bang. Okay. So let's do this one. This is a register that is built into the ALU, where we know what that is straight away, the accumulator. This is a register that holds data or an instruction that has been fetched from memory, where we know what that is. MDR is data or instructions, that's what it's holding, so we know it's MDR straight away. It could be the CIR, but it says that it's just been fetched from memory. This carries the addresses around the CPU. Well, uh-oh, I haven't mentioned anything to do with that. So anything which carries, we know it could be a bus. So it could be the data bus, address bus, or the control bus. So which bus is it going to be talking about? If it's addresses, it's the address bus. Okay, that's the easy part. Let's do the hard part now. What is the description for all our registers? Well, it's holding, it stores. So stores the address of the data or instruction that needs to be fetched from memory. Stores the address, and I'm going to put temporarily. Stores temporarily. Program counter. I can put stores the address. It's basically a copy of the next, but it could also be the current, because I'll show you what I mean by that in a minute. Instruction data to be fetched. When I put fetched, I'm going to put /processed, because that's the end goal, for it to be processed from memory. Okay, so what do I mean by current? Well, here's the thing. If you've got a program counter and it's 1, and it goes to the address 1, and it goes to the MDR, whatever the data is, that is now the current. Then the program counter goes up by 1 increments, so that'll be 2, so that will now be the next one which needs to be executed. So it could be current, or it could be the next. It doesn't matter. If you put both, brilliant. The control unit. Okay, this sends control signals to control flow of data in CPU. You can also say it manages the execution of instructions in CPU, including the decoding. So that's a lot of things. Basically, you've got your CPU, the control unit manages when the data is sent from one register to another register to then the address bus. So it controls the flow of that data. But it also manages the execution of the data and instructions. So, for example, it handles the decoding aspects within the CPU. So that's 2 different aspects you can talk about. Pause the video, give this question a go yourself first. I'll do the answer in 5 seconds. 1, 2, 3, 4, 5. We're part of a CPU that carries out calculations. Well, we know that is going to be the ALU. If you put ACC, you're wrong. The ACC stores the data which is going to be calculated as a result of that, but not what carries it out. It'll be the ALU which carries out any calculations. Okay, so Pause the video, give this question a go yourself first. I'll go over the answers with you once you're done. So how would I go about this? Well, I would normally do the ones I can definitely do first and then process of elimination. So I'm going to go through these. ALU, that should be quite easy. I'm going to look for anything to do with calculation. And there we go. That's my ALU done. Boom, boom. Buses I'm going to come back to control unit. I know that manages the flow of data around the CPU. And there we go. Done. Done. IAS, I'm going to come back to input and output devices. Like a keyboard is an input device. An output device is like a monitor. Something we can see the result of. Input affects our computer. So what allows us to have interaction with the computer? There you go. Perfect. Registers, we know that they temporarily hold data, instructions, etc. So anything with temporary in, there we go. Easy peasy, lemon squeezy. So that leaves us with buses. Used to connect together the components of the CPU. Yes, but it's not just the components of the CPU, it's also components outside of the CPU like the RAM. IAS is our memory which holds data before they're processed. So we hold in our RAM our instructions and our data goes to the CPU for it to be processed, as in fetch, decode, and executed. So it stores it before. It also stores the results after as well, but we'll talk about that another time. I think that is done. Happy days. Okay, so identify components which are part of the CPU. This is easy. Just do a dump and then pick your top 4. If you're not sure, go with the easy ones first. So I'm going to do MAR. I'm going to do my registers, MDR. I'm going to do my program counter, and I'm going to do, you know what? I'm going to throw in another component as well, which is not a register. Let's do the ALU. You could talk about the different buses. You can do the control units. Or you can do the other registers. What you can't do is RAM. RAM or main memory is not a part of the CPU. If the question said identify 4 registers, one of those is wrong. And that would be this one here, because that's not a register. It's just a component in itself. Okay, so we've got another sort of question like this. Pause the video. Okay. I'm hoping you're going to go yourself first. Let's go for the ones which I can actually definitely do. The memory address register. Stores the address of the input device. No, I don't recognize that. It's a bit weird. It just talked about address, but what the heck is that? Stores the address of memory location about to be written or read to. Yes. Perfect. I can do program counter. Okay, now you might say, how do I differentiate between these two, this and this? It's quite simple. Program counter's job is to get the next instruction. That's going to be fetched. But we could end up where instead of loading something, we could end up with saving something from the CPU back into our RAM. It needs to go into the correct memory address location. Therefore, we need to get that from the MAR. So the MAR stores the address of what something's going to be loaded from or written to. Loaded, read, written to, saved. So for example, if I'm playing a game and I press Control plus S, beforehand I loaded it and it was in address location 1, the game. I'm making this really simple, by the way. So we loaded it. We do some stuff in the game, we press Control S to save. It needs to, now the new version of the game, the updated version, needs to go into the same address location, so it can be saved or loaded from in the MAR. That's the job of the MAR, to store that information so we can remember where it goes, where it's come from, where does it need to go, if we need to send it back. The program counter is just about the next instruction to be fetched. Alright, we need to fetch from the address 3 this time. It doesn't care about saving or loading, it's just the next one to be fetched. Fetched would be read. Memory data register. This is stores the instruction that is to be decoded? No, we know that is the CIR. Stores the data that's just been read from memory and is about to be written to memory. Yes. So, as I said to you before, what's the purpose of the MDR? The MDR is to store data which has come from the RAM to the CPU. So it stores that instructions or data which has just been read, loaded. But also, in the MDR, it could take whatever's been changed, like in the ACC. So it used to be that, now it's that. And it's going to save it or write it back into RAM, but it needs to go through the MDR first. So for example, as we just said, let's imagine my character in a game has gained an extra life. They used to be on 0 lives, now they're on 1 life. In fact, let's say they used to be on 1 life and now they're on 2 lives. So if I was to clear that, it used to be in the accumulator 0001, they've gained an extra life, so it's now going to be that. It then gets sent to the MDR then sends it back to the RAM, and it gets put back into the address location like 1, which is lives, and now it's remembered I've got 2 lives in my game. So the MDR stores data which is to be fetched for it to be processed, but it also stores data which has been processed and changed and writes it back to the RAM. So the MDR is very important. I think we're done. Okay, you know the drill. Pause the video, give this a question and go yourself first. I'm then going to go over the solution with you. So MAR, what is the role of this? Well, it stores the next address to be fetched from RAM, main memory. It is temporary. It receives it, so I'm going to give it some background. The address from the program counter, address bus fetches data from address location. Nice and easy. So that is the job of the MAR. It stores the next address to be fetched from RAM. Main memory is temporary. It gets its address from the program counter. The address bus will then go and fetch the data from that address location, and then we go into the MDR. Stores data from the address fetched from MAR to MDR. So it stores the data where the address bus fetches it from the MAR's pointing. MAR so it goes to address location 2. The address bus will drive to address location 2. It'll fetch the data inside, and it'll basically store it in the MDR. Copies instruction, or should I say data, to CIR where it is decoded. It can also, when data needs to be written, as we discussed many times, the changed data in the ACC is copied to MDR to write, let's say send back. Sorry, didn't mean to do that. Send back to RAM or main memory. So not only can it store data which is fetched, it could also if we change something from the ACC, as I keep saying, it's changed. It used to be 0000, it goes to MDR. From the MDR, it will then go back to the RAM in like that address location. So it has two roles. One for when we're reading, so it stores the data from the MAR / instruction, where it goes to CIR, which will get decoded, and it can also, when data is being written, go from the ACC into the MDR to the RAM. Okay, so what do we actually mean by register? Well, register is small, fast memory. That's what it is. It's a little piece of small memory, like the MAR, which lives, literally is part of the CPU. It's temporary, stores address, data, instructions to be processed or has been processed. Pause the video, give it a go yourself first. Okay, so we've got data bus and we've got the control bus. The data bus is responsible for fetching data from the RAM or writing data back to the RAM. Transmitting. So it's responsible for transmitting data / instructions between main memory and CPU. So this question isn't really going into too much depth about what the buses are about. It's just like a quick overview. We've then got the control bus. So you've got, again, the CPU and you've got the control unit. The control unit is responsible for the signals within the CPU itself. You've got the RAM, you've got your buses, and you've got one of its buses being the control bus. The control bus is responsible for the control bus is responsible for all the timing signals for components outside of the CPU to work with synchronizing with the CPU, like the buses, for example. So responsible for transmitting, so it transmits control signals. Let's do external, not outside. External to CPU. Okay, so let's give this a go. It should be pretty easy. Let's do it based on the bus. Address bus. No, not signals. Not exchanging data. Relating to memory addresses. Yes. It's unidirectional. That basically means it just goes in one direction. It just goes from the CPU, one direction, to the main memory, the RAM, with the address location on it, like address 2. That's it. That's all its job is to do, to go to that address location. It doesn't need to go back with anything. Obviously it does drive back if you think of a real life bus, but it doesn't carry anything with it. It just goes back to the CPU again. So it's one directional, unidirectional. Uni meaning one direction. Unification, one. Control bus. Carry signals to coordinate computers' activities. Yes, I spoke about that in the last question. Data bus, bidirectional. between the processor, memory input and output devices. So not only does it go to the RAM, it also takes in any, if I press a key on a keyboard, it'll be the data bus, which will then need to communicate with the CPU that I've done that. So bidirectional, why is it bidirectional? Well, remember what we said about the data bus. Its job is for reading and writing. Why is that going back to the pen? So let's give it a 2. You know what? Sub this. Let's do that. Okay, so if we are loading something up, the data bus will go from here and take the data to the CPU. But if we're saving something or writing something, remember it goes from the ACC, it'll go to the MDR, from the MDR, the data bus will go in that direction and dump it back into the RAM, the main memory, like a new life which we've gained in the game. So it can go in both directions, this way to save and this way to load, bidirectional. Okay, so let's give this a go. It should be pretty easy. Let's do it based on the bus. Address bus. No, not signals. Not exchanging data. Relating to memory addresses. Yes. It's unidirectional. That basically means it just goes in one direction. It just goes from the CPU, one direction, to the main memory, the RAM, with the address location on it, like address 2. That's it. That's all its job is to do, to go to that address location. It doesn't need to go back with anything. Obviously it does drive back if you pick up a real life bus, but it doesn't carry anything with it. It just goes back to the CPU again. So it's one directional, unidirectional. Uni meaning one direction. Unification, one. Control bus. Carry signals to coordinate computers' activities. Yes, I spoke about that in the last question. Data bus. Bidirectional. Between the processor, memory input and output devices. So not only does it go to the RAM, it also takes in any, if I press a key on a keyboard, it'll be the data bus, which will then need to communicate with the CPU that I've done that. So bidirectional, why is it bidirectional? Well, remember what we said about the data bus. Its job is for reading and writing. Why is that going back to the pen? So let's give it a 2. You know what? Sub this. Let's do that. Okay, so if we are loading something up, the data bus will go from here and take the data to the CPU. But if we're saving something or writing something, remember it goes from the ACC, it'll go to the MDR, from the MDR, the data bus will go in that direction and dump it back into the RAM, the main memory, like a new life which we've gained in the game. So it can go in both directions, this way to save and this way to load, bidirectional. Okay, so pause the video, give this question a go yourself. Identify one, oh this is easy, identify one bus and explain its purpose. Well, we talked about the data bus. It transmits data between components in the CPU. We talked about control bus, so it transmits control signals from the control unit to other components in the CPU. The address bus we can talk about now. Transmits, or we can say carries, address location between CPU and main memory. Easy. Okay, so this final question is an A-level question. Pause the video, give it a go yourself first, but try and use the knowledge you've learned already from previous and from this video also to see if you can solve it. So we need to label the 3 buses A, B, C. So this is the CPU, the registers, we've got this line going this direction only, so unidirection to main memory. Well, we know straight away that's going to be our address bus. We've got this one, we've got arrows on both sides, but it's connecting the registers to main memory, so we know that's going to be our data bus because it's bidirectional. And then we've got A, which seems to be linked to the control unit, our CPU clock, and our main memory, and that will be the control bus, because the control bus works with a control unit for the timing signals, and it uses the system clock to manage these timing signals. So the control unit controls the flow of data inside the CPU. The control bus controls the interaction with all the components outside of the CPU using the system clock in the CPU. So they work together, the control unit, the control bus, and this system clock. The clock is basically like Big Ben inside your computer. Before I say anything else, pause the video, give these questions a go first. Okay, when we talk about stats of a CPU or performance of a CPU, we talk about two things. We talk about clock speed, and we talk about cores. Now, what is meant by a core? So, here's the thing. This is our CPU, and I'm going to make this really, really simple, not technical, but really simple. Our CPU has one core which can do fetch, decode, and execute. So when it fetches one instruction which then can be executed. So the purpose of a core is to process an instruction using a Fetch-Decode-Execute. To do FDE. That's the purpose of a core, to allow us to do Fetch-Decode-Execute. If we have 0 cores, we won't be able to do any of that. So, one core. Why does that undo work? That's so weird. I can't press undo. Let's just try this instead. Nope, doesn't want to undo that either. Whatever. Okay. We then upgrade the computer to dual core. Dual means 2, quad means 4. So how does that affect our performance? Well, it's going to increase our performance. How? Well, we have our CPU, but now it's got dual core, so CPU, so 2 cores. Fetch, decode, execute, fetch, decode, execute. That means it can get an instruction here, and this can also deal with an instruction to do fetch, decode, execute at the same time. So increase performance by simultaneously, that means at the same time, or at the same time, simultaneously, processing 2 instructions at same time. By me saying simultaneous, I don't mean to say at the same time, but whatever. If it was quad core instead of dual, so it said quad core in the question, fetch, decode, execute, fetch, decode, execute. It'll increase its performance by seamlessly processing 4 instructions at the same time. There you go. That's what happens when we upgrade. We can deal with more instructions at once. Okay, pause the video, give a question you go yourself first, I'll then give you a solution. Okay, so to answer this question, we need 2 things. Number 1, what's the purpose of clock speed? And then what happens when we improve it. So clock speed is, imagine we've got our fetch, decode, execute cycle. I want you to see how fast I'm fetching, and then decoding, and then executing right now. I am going to the RAM to fetch the address, to fetch the data from the address location. The data is then being sent back to my CPU where it's going to be decoded. Control unit is now decoding it in the CIR. We're now passing it to ACC where we're going to deal with any calculations for it to be executed. We're then going there. That's quite a slow clock speed. If you increase the clock speed, fetch, decode, execute, fetch, decode, execute. We can deal with more instructions per second. So imagine this happening in milliseconds, and we can speed it up and speed it up and speed it up and speed it up. Every time we do this, we deal with something else. We deal with another instruction, save, quit, open, jump, duck, shoot, gun, press A, whatever. So the purpose of what is clock speed? It's the number of fetch, decode, execute, or instructions that can be executed per second. That is clock speed, the number of instructions that can be executed per second, or cycle, fetch, decode, execute cycles that can be executed per second. By increasing clock speed, increases amount of fetch, decode, execute cycles, which means more instructions. I can't write. I've written a lot today. Can be executed per second. So you've got cores, clock speed, and this affects performance of computer. If we increase cores, what can that do? If we increase the clock speed, what can it do? You need to be aware of both.